Hey guys, I wanted to go through on our last day, go through a couple of the homework problems that probably posed a significant difficulty, like number 29 and number 32. Those are pretty tough ones. If you're not prepared to do like the algebra side of them, it can be rather difficult. And I might even throw 31 in there just for fun. At the end, I'll discuss kind of the alternative to the limit one we've just shown you. There is actually more than one variation on the slope generating function. The other one, some people love and some people just despise. Some people think the second one is a lot harder than the first one. And others, especially if you're really good at factoring, some others think the second one is the easier of the two. Because if you can factor well, you can have a much easier time solving it. If you can't factor well, then you start getting into some trouble. The one we showed so far, this one we're going to use today as well, the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This one's the general one, the one that everybody is taught and is taught how to use and uses the most. There is an alternative. This is the alternative. It is the limit as x approaches c, or in this case c is the value you're actually trying to find it at. So if you're trying to find it, at 2, you'd make the limit as x approaches 2. And then you do f of x minus f of c over x minus c. And just like with the previous one, how you're going to have to go through the process of trying to figure out how to plug in f of x, how to plug in f of c, and then dividing by the x minus c, and you're going to keep getting 0 divided by 0 until you simplify algebraically. That process isn't going to change between these two, because these are going to generate the same solution. It's just, well, this one is kind of like a sledgehammer. It has a lot of uses if you're trying to take down a house, but it may not always be the best tool. This one is more like a regular hammer. It's very good for certain jobs, but for other jobs you would never want to use it for. So let's look at 3 of the problems from last time. 29, 31, and 32. Number 29. This is one that's going to be forced to use the conjugate. So we're trying to find f of x equals the square root of x. And in this case, the point we're trying to do it at is the point 1, 1. So let's go ahead and go through the process. We start by doing the limit as delta x approaches 0. This is one where doing it the other way is actually kind of painful. I strongly recommend against it, but you do you, I guess. Is equal to, so we do the square root of x plus delta x minus the square root of x all over delta x. And just like last time, how we end up for these kinds of problems using a conjugate. We only do a couple of these over the summer because it's the end, but you will end up doing a lot of these in your regular class, so look forward to that. We're going to use the conjugate, which is the square root of x plus delta x plus the square root of x and the square root of x plus delta x plus the square root of x. So we use the conjugate. Remember, you're going to simplify the top but not the bottom. So we'd have the limit as delta x approaches 0. On bottom we'd have delta x times these radicals, x plus delta x plus the square root of x. On top, these radicals end up canceling, meaning we have x plus delta x minus x. The reason they cancel is because the conjugates always force difference of squares. That's why you use a conjugate in order to make that work. Now from here, simplify again. We limit as delta x approaches 0. On top, we end up with delta x, because the x and the negative x are going to cancel. On bottom, we have delta x times square root of x plus delta x plus the square root of x. And so you can see how those delta x's are going to end up canceling. And then we end up with the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus the square root of x. We can then actually plug in the delta x is equal to 0 because we no longer have 0 divided by 0. Again, you can check that throughout to make sure I'm right, but I am. This becomes 1 over the square root of x plus 0 plus the square root of x. Square root of x plus 0 would be the square root of x. The square root of x plus the square root of x would be 2 square root of x. Meaning this is my slope generating function for the entire function, the square root of x. This is the slope generating function. So we want to find specifically at that point, so at the point 1, 1, which means that we take the x value and we plug it into that slope generating function, which gives us a slope of 1/2. This is the slope at that particular point. Now, to find the tangent line, which was what the question asked us to do, we got to take that equation, which was y minus y1, which is 1, equals m, which is the slope, 1/2, x minus x1. And so this is the tangent line of that function at that point. Once again, let's look here at our math before we go to Desmos to verify our results. The original function was the square root of x. We plug into our big formula, which would be the square root of x plus delta x minus the square root of x over delta x. We multiply by the conjugate. The conjugate forces the top to get rid of the radicals and makes the bottom kind of nasty, but that's okay. We simplify the top, ends up being just delta x, which means the delta x on bottom can cancel, leaving this new limit. We can then evaluate the limit by plugging in 0 for delta x, because we no longer end up with 0 divided by 0. And that's going to equal to this function, which simplifies to this. Now this is the overall slope generating function. At a particular point, we have to plug in the x value, so we take the 1 from the x value, we plug it into our function, giving us this particular slope. We then take the slope and plug it into the tangent line, and there's my tangent line. I can verify that using Desmos. Let's pull it up. Desmos, I would need the original function, which is the square root of x. There it is. So we're looking at this point right here. Okay, so let's put that line in. I'm not going to bother simplifying because I don't have to. Equals 1/2 x minus 1. And you can see how these two, they meet up at 1, 1. And this clearly represents the slope at that particular point, which means this looks perfect. And so this is in fact our slope generating function. And we did in fact find the slope, which gave us this tangent line, which meets all of our criteria. Again, you might have gone ahead and simplified this, but it is not required. All that's required is you get this formula. You get the tangent line. If you simplified it down to, y equals 1/2 x plus 1/2. Yeah. If you simplified it down to that, great, good for you. It doesn't matter. You just did more work. Okay? Let's go ahead and look at number 31. Same way. Here it is. Number 31 has a unique function, which makes this kind of fun. On 31, since it's not a radical, you're not going to use a conjugate, but you will use something. Here we go. Limit as delta x approaches 0. And my function was x plus 4 over x. Okay, let's do it. So, in this case, I would have x plus delta x plus 4 over x plus delta x. So this is my f of x plus delta x minus my f of x, which would be x plus 4 over x all over delta x. Okay, now I'm going to start doing some algebraic simplification before I go any farther. For example, I can distribute this negative sign. But once I do, I kind of get in a spot where I'm kind of sort of stuck, and so we'll see where it goes from there. Limit as delta x approaches 0 of, let's see, we distribute the negatives, this becomes negative x minus 4 over x, and that would mean that this negative x and that negative or positive x are going to cancel, meaning I end up with delta x from the first parentheses plus 4 over x plus delta x minus 4 over x, because we distribute the negative, all over delta x. That's not too bad. But if I plug in 0, I actually still end up with 0 divided by 0. So I know I need to fix something in here. And to do that, I'm actually going to use a very specific multiplication. I'm going to attempt to rationalize these denominators, which means that right now I do not want to have an x plus delta x in the denominator. I do not want to have an x, so I'm going to multiply by x plus delta x to the entire function. That's going to cause this fraction to disappear here in the middle, but it's going to force the other two to change. I'm also going to multiply by x for the same reason. I do not like having what are called complex fractions. That's when you have a fraction inside of another fraction. I'd rather not. And so we're going to get rid of them using this particular fraction. It gets rid of them by, when we distribute, you have to multiply these to each one. When I multiply the 4 over x plus delta x times x plus delta x, the x plus delta x's are going to cancel, leaving just a 4 behind. A very roundabout way of saying I'm simplifying a bunch of stuff. Limit as delta x approaches 0. And we end up with, if we distribute this, we would take x times delta x and get x delta x times x plus delta x. So the first one doesn't simplify at all because you just take the top and multiply it to the x plus delta x plus the 4. The x plus delta x on bottom and the x plus delta x over here will end up canceling, which makes this become 4x. And then I have to multiply this through. The x is going to cancel, meaning we have minus 4 times x plus delta x. All over, on bottom we'd have delta x times x plus delta x times x. Ooh, like I said, there's a lot of algebra here. If you're not comfortable doing this kind of stuff, you have a couple months to get ready. Take your time, look for these different properties to figure out how to simplify these complex fractions. This is a common one in algebra to use, so make sure you learn it. Limit as delta x approaches 0. I'm going to start simplifying some stuff. So things that I can simplify. I can distribute this to both pieces. This would become x squared delta x plus x delta x squared. So take this x delta x and distribute it to each one. When I distribute this, it will become negative 4x minus 4 delta x. And the cool thing that happens there is the 4x and the negative 4x are going to end up canceling, meaning it would just negative 4 delta x. All over delta x times x plus delta x times x. If I plug in delta x is 0, the top becomes 0, the bottom is still 0 because 0 times anything is 0, so I know I'm not finished yet, but I am very close. I can see that there's a delta x on top in each term, so we're going to factor that out. So we do the limit as delta x approaches 0 of delta x times, this will be x squared plus x delta x minus 4 all over delta x times x plus delta x times x. Okay, I can cancel out those delta x's, leaving me the limit as delta x approaches 0 of x squared plus x delta x minus 4 all over x plus delta x times x. Now, if I plug in 0 here, I get 0 on top, 0 on bottom, not allowed. If I plug in 0 here, though, I do get an answer. I end up with x squared minus x times 0 minus 4 over x plus 0 times x. And this ends up becoming, on top we have x squared minus 4. On bottom we have x times x, which is x squared. Which means this is my slope generating function. So, how do I actually find the slope? Well, I gotta plug into this thing. Now, in the original problem, the number we were looking at was at the point 4, 5. So what I can do is I can plug 4 into this function and get a number answer for my slope. So I'm going to plug in 4. So at 4, this thing will become 4 squared is 16, minus 4 would be 12. 4 squared on bottom would be 16. 12 divided by 16 would be 3 over 4. So that's my slope. apologize for running out of room here. That would make my equation y minus 5 equals 3 over 4 x minus 4. There's my final answer. Whew. So notice how we had to use a specific algebra trait in order to get rid of those fractions inside of a fraction. That trait is really useful to have, but you have to apply it correctly. Remember, it's distributive property. You got to apply the x to all three pieces. You got to apply the x plus delta x to all three pieces. And some of them end up canceling, and some end up not canceling. You could also, once you're here, you then have to algebraically distribute to both pieces, and then simplify algebraically, allowing you to factor something out to cancel it, and then allowing us to actually apply the limit and get to a solution that gives the slope generating function. Once you have the slope generating function, you do not have the slope yet. You have to go through and actually find the slope, which is done by plugging into this function. So we had to plug 4 in. That's where we get the 12 over 16, which becomes 3 over 4. And even then, if the question asks for the tangent line, you're still not finished because all you found is the slope. Thankfully, once you get the slope, you can just plug all those pieces in, and then you got the tangent line right there. Slope Desmos. My equation was x plus 4 over x. It's a pretty unique function. In this case, the point in question they're asking about is this 0.45. So we want to find a tangent line at that point. Let's see if we got it. The equation was y minus 5 equals 3/4 x minus 4. Look at that beauty. Goes through 4, 5, and it appears to match the slope at that point, which tells me we did something good here. So there we have it. That's how it's done. 32 is done pretty much the same way. The only difference is it's a little simpler. I will say this as we go back. One of the neat things about the calculus part of this is the calculus is independent of the algebra. So my original equation was x plus 4 over x. If there is another equation that is equivalent to this, for example, if I had taken that first fraction and turned it into x squared over x, which I just do by multiplying that first fraction by x over x, and then I combine those two together to get x squared plus 4 over x. Since this equation and this equation are the same, their slope generating functions will be the same. But maybe one of them is easier to solve than the other. You won't know until you try it out. It turns out they're both about the same for this one, but sometimes, if you algebraically simplify, you actually get to an easier problem, which can then be solved with better methods. And so make sure, because this process can be difficult, it can be long, you have to be working with the best possible equation. So look to see if there's a way to rewrite it that maybe makes it easier. If you find that you're struggling with the way you have it written now, maybe you get to this step and you're like, I'm not sure what to do. Maybe go back and see if maybe you could rewrite it, and maybe you have a better way of approaching it. Who knows? You will never know unless you try it. So make sure to go out there and see what you can do with that function. Now, the alternative we talked about. I will post an assignment for the alternative, but it is not required at all. I will do a couple of examples using the alternative because it requires some factoring stuff. But if you're good at factoring, and for certain equations it works fantastic, it's just an alternative. So let's take a look at some of the problems that I posted for tonight as optional problems that you can try out. So for example, number 73. This is your first one. Okay? It says f of x is equal to x squared minus 5. And the point in question we're trying to work with is c equals 3. So we're going to use this alternative form in order to solve this problem. Now it's just different. It's not better or worse. For certain problems it's better. For certain problems it's worse. You won't know until you try it. So let's take a look at this limit. We're going to do limit as x approaches 3, because remember, we go to the number that we are approaching, which is 3. We need to do f of x, which is x squared minus 5 minus f of c, which would be 3 squared minus 5 all over x minus 3. And so we've taken everywhere there used to be a c, or everywhere there used to be an x, we replaced with our number c, which is 3. So instead of x squared minus 5, we have 3 squared minus 5. Instead of x minus c, we have x minus 3. Now, we do our algebraic simplification. X squared minus 5, limit x approaches 3. Minus 3 squared is 9, minus 5 would be 4, so that would be x squared minus 5 minus 4 over x minus 3. This would become the limit as x approaches 3 of x squared minus 9 over x minus 3. Now you can see that if I plug in 3 at any point in time, I end up with 0 divided by 0. So nothing has really changed compared to the old one, right? We still constantly end up with 0 divided by 0. But the difference is, if you're good at factoring, you can see what's going to happen at the top here. This becomes the limit as x approaches 3. We factor the top to become x plus 3 times x minus 3 all over x minus 3. We can then cancel the x minus 3 and x minus 3, leaving us with the limit as x approaches 3 of x plus 3. We could then now actually apply that limit and plug in 3, which means we end up with 3 plus 3, which is 6, which tells me that this is the slope of that graph at x equals 3. It's just an alternative way of doing it. And if we apply this with the other method, we would get this exact same answer. But if I want to just find the slope once, this one's pretty decent. Like, it goes by quickly. But for other problems, it's really not. Like, I would never want to do this with another problem. For example, let's look at the problem, one similar to the problem we have, like 78. We're trying to do f of x is equal to 2 over x, and the c in question is at 5. So we're trying to see what's happening at 5. So let's apply a limit. Here's a limit as x approaches 5 of, and now we have to apply that little function. So we have f of x, that would be 2 over x, minus f of 5, which would be 2 over 5, over x minus 5. And you can see how you end up with fractions instead of fractions, which you're going to be forced to simplify. It doesn't get any easier just because the function is different. It's just, you know, a different function. And so just like before, we're going to be forced to use 5 and x on top and bottom in order to get these fractions to disappear. This ends up becoming, let's see, 5x times this would become 10x over x, minus 5 times that would become 10x over 5. And on bottom we have x minus 5. These end up canceling on top. So the limit as x approaches 5 of, let's see, 10x over x, the x's would cancel, leaving just 10. 10x over 5, we're going to become minus 2x over x minus 5. And then from here, I'd have to factor some, which I can do. Limit as x approaches 5. I would take a negative 2 out, making this become x minus 5 through some fancy algebra. Because this actually lets me get to my answer a little faster. Canceling those, I get the limit as x approaches 5 of negative 2. Remember, the limit of a number is just the number. So that tells me that for this function, the slope at 5 is negative 2. And so it's just a different process. And you notice that it's shorter for some of them, but it is not always shorter. It's just different. And so you have to be careful, because there are now 2 ways you can approach these problems. You're welcome to practice this way. When it comes to your post-test, you're welcome to use this formula if you wish. All I asked on your post-test was determine the tangent line. which means that if you can use either method to find the slope, just make sure to plug it into the line formula. That'll be it. That's the last thing we have to talk about for the year. No matter what, I hope you guys enjoyed this summer. I know it would be a little difficult to enjoy since this is not where we were expecting to be. But I really do hope you got something out of this, that as you go into your next math class next year, that this is a little bit helpful. I will have my YouTube channel open, so you can always come back and review some of these videos if you want a little bit of help. And you guys have my email address. If you ever come across questions throughout the year that you're just not sure about, shoot me a message. I do not mind, because at least then I know you're getting something out of the class. That'll be it. I wish you the best of luck as you continue your mathematical journeys, and I will see you guys some other time.